Okay, kids, we're back and we're moving on to 7.5 here, a very important experiment. But before we get there, let's go over some of the material we looked at yesterday, but really focusing in on the electric field between two parallel plates. One side is positively charged, the other side is negatively charged. So picture like two playing cards in a sandwich-like situation, one on top of each other, or one left, one right, and one's positively charged and one's negatively charged. We know from our previous discussion that the electric field in there is constant. I even showed you a simulation of that. We know it's constant. Now, if you were to put a little purple ball here, positive, it represents a positive test charge. This positive test charge would be repelled away from the positive plate and attracted towards the negative plate. And remember, small positive test charges is how we map out electric fields. So since it would experience a force towards the negative plate, away from the positive plate, that's why this constant electric field has the direction away from the positive plate towards the negative plate by the definition created of using a small positive test charge. So let's say we've got this small positive test charge here. There's an electric force on it, pulling it towards the negative plate. And let's say I put onto it an applied force to move it in the other direction. So I'm going to move it in the other direction through a displacement, delta D. So from here, let me try to get another icon here. From here, it's going to be moved to here. That's its displacement. And I'm going to call that displacement from here to here to have a magnitude of r, and it's going to move without any acceleration. Very important technicalities here if we're going to understand what's going on. So a few things I want you to remember from a while ago. The electric field was defined as the electric force per unit charge. That's how we defined it. You can go back and look in your notes. If we rearrange this equation, we get force electric is equal to Q, the charge, times the electric field. Look familiar? Look at this. Look at the similarity. When you have constant fields, force of gravity is equal to the mass times the constant gravitational field. Right? Force of gravity times mass. Gravity is all about mass times the gravitational field. Force electric equals the charge. Electrical forces are all about charges. The charge times the electric field. Look at the similarity. Amazing. So that's one thing I need you to remember from our past work. The other thing I need you to remember is the definition of voltage or electric potential. It is equal to electric potential energy per unit charge. So we've got this fundamental equation here. If you want a change in the voltage, well, that would be a change in the electric potential energy, and you would still have charge in the denominator. So voltage change is equal to an electrical potential energy change per unit charge. If we rearrange this, we get change in electrical potential energy is equal to the charge times the change in voltage. So if you're not sure about any of this, this is a very important time to go back and look at your previous notes and your previous work to get this understood. Next, let's calculate what is the work done by this applied force as it's moving this positive test charge towards the positive plate. This is very similar, ladies and gentlemen, where you would be lifting a ball upward in our classroom against the gravitational field. Here, I'm lifting, I'm using the word lifting quite liberally here, a positive charged particle against not the gravitational field, but against the electric field. But the similarities are there. So work is defined as magnitude force applied times the displacement. I've gotten rid of the cos because look, the applied force and the displacement are in the same direction. It would be cos of 0, which is 1. And I've used that there's going to be a change in electric potential energy, which is equal to Q times delta V. There's a change in electric potential energy because I'm pushing this positively charged particle against the electric field. Very similar to lifting a ball in our classroom to a higher elevation against a gravitational field. So when you're lifting a small ball against a gravitational field, you're going to change its gravitational potential energy. Similarly, if I'm lifting, in quotation marks, a positive test charge in a constant electric field and I'm going against that electric field, there's going to be a change not now in gravitational potential energy, but there's going to be a change in electric potential energy. And I'm using this equation right here to replace change in electric potential energy times Q, the charge that this object has, times the change in voltage. Let's continue. So the force applied equals the electric force. Why? Because the acceleration is zero. Those two forces are equal in magnitude but opposite in direction. So that's why I made the change here. I changed the magnitude of delta D just to R, and the right side of the equation continues. Now I remember that force electric is equal to how much charge that particle has multiplied by the electric field that it's in. And in this case, the electric field is constant. That's how I made the change here. I'm going to drop the magnitude signs and I get Q. Electric field magnitude R equals Q times the change in the voltage that the charge experienced as it went through its displacement. And that leaves us with the electric field times R is equal to delta voltage. This is very important, and it's a new general equation we have to have. So in general, for parallel plates, here's the electric field, it's constant. The electric field always points from positive to negative. Let's say these parallel plates are divided by a distance r. So we're not only doing a portion within it like we did in the experiment we just did, we're taking r to be the complete distance across from one plate to another. When you have that, then you can calculate that the voltage difference from one side of a plate to the other would be the electric field that is constant that exists in here times R. Or if you want to rearrange this, the electric field is equal to the voltage change divided by R. So that leads to a very interesting situation because usually electric fields were described as newtons per coulomb. But now electric fields can also be described as volts per meter. It's a equivalent unit. They both work depending on the context. All right, now this is what I want you to do, and listen very carefully. At this point here, I want you to pause the video before we move on to the next part of this video note lesson I'm giving you. And I want you to watch this video that I've put a link into because it's going to be a very good introduction to the next part of this lesson. If you don't watch this video and then you come back and look at what I'm trying to teach you in the next part of this lesson, it's going to be more difficult for you. So pause the video, take the time to watch this video, and then we'll come back. Thank you. Okay. All right, we're back, and I hope you watched the experiment about the great Robert Millikan. What a brainiac. Amazing. So let's try to replicate that a little bit here. Here's a positively charged particle. Okay. Here is a plate that is positively charged at the bottom and negatively charged at the top. And let's say that we know the voltage difference between one end and to the other end. We know the delta V across there. So many volts of voltage difference between the two sides of the plate. And let's say now that the plates are separated by a distance delta X. All right, instead of R, we're going to use delta X. They're so many meters apart. We remember that in here, the electric field is constant. So a couple things to remember. The electric field is related to the voltage difference across the plates by magnitude of the electric field is the voltage difference divided by R, how far they are separated. Or in this particular case, it's not R, but delta X. All right. And we also remember that the electric field is equal to the force that a particle is experiencing divided by how much charge is in that particular particle. These are all things we have to remember. So what did Millikan do? Well, Millikan realized that if he's got an object that is just floating and not moving upward or downward, that the electric force upward and the gravitational force downward must be equal. And he remembered that the force of gravity is the mass times the gravitational field. Similarly, the electric force is the charge times the electric field. See how these two are quite similar? Amazing. But he realized that these two forces were acting on an object that was not accelerating. That equals 0. So we can put in what these equations are for each of them. QE plus mg equals 0. I bring this to the other side. All right, I bring it to the other side. Then what I do is I realize that the electric field here is equal to the voltage difference across the plate divided by how far you are going across the plates. So I put that in. All right. Then what I do is I rearrange this and I solve for Q. So what Millikan did is he knew the mass of the oil droplets because oil had a known density. He could measure how big the droplets were, so he could figure out what the mass was. He knew what planet they were on. We were on, okay, and he knew how far apart the plates were, how far apart the plates were, and he also knew the voltage difference between them because that's something he could change on a controller, on a knob. He could change how much voltage difference was between them. And he could then calculate the charge on the plate. Excuse me, the charge on the particle, not the charge on the plate. The charge on the particle that was just floating there. It wasn't moving up, it wasn't moving down. And he did this many, 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 many times. And what he found was that charge on all the particles, all the oil droplets, was always a multiple of 1.6 times 10 to the negative 19 coulombs. And this became known as the elementary charge. And that is the charge that exists on all electrons negatively, and that is the charge that exists on all protons positively. So anytime you want to find the charge on an object, it's always equal to some whole number, 1, 2, 12, a million, right? Times the elementary charge, the charge carried on the electrons that were lost or gained from that charged particle. If an object has extra electrons and excess of electrons, it's going to be a negative charge. If a particle has lost electrons, there's a deficit of electrons, it's going to be a positive charge. But whatever particle it is, its overall charge is always a whole number multiple of the elementary charge. So there we have it, kids. I'm going to give you some questions to do, to work on. I hope you enjoyed the video. That's good. Um, what I'm going to do now is try to let you see an animation, a simulation here. And what we've got here is a positive plate, a negative plate, and a particle here. All right. And what Millikan was actually doing is, you see how this particle is falling? So those forces aren't equal. So he was literally trying to change the electric field until it was the voltage and therefore the electric field until it balanced gravity. It's not as easy as you think. Yeah, getting close there. Oh, not quite. But he was trying to balance it so the object wouldn't move. Almost had it there. That's pretty darn close right there. But that's what he was trying to do. He had a knob that changed the voltage and therefore the electric field. I don't know if I'll ever be successful at this. Anyways, play around with it. You probably have more sensitivity than I do. But this is what Millikan was trying to do. And I've put this link on today's page. So play around with it if you got time. Okay? You guys take care. Bye-bye.